So if this is our conservation of energy setup, the first thing I hope you recognize is that as box 1 descends, box 2 has to ascend. So I'm going to call this 1 and this one 2, and I'll use that throughout the problem. At the beginning of the problem, the system is at rest. But after the boxes have been released, this box is moving downwards and this box is moving upwards. Fair enough? Any question about any of that yet? If we consider this a conservation of energy system, meaning that there's no external force acting on the system that took energy away. Kyle brought up that there was forces acting in the system last class period and wondered why they didn't do work. They do work. There's other forces doing work in the system. The tension does work. But we're not asking about the amount of work done. We're asking about the energy in the system and how that relates to the velocity of the system after it's been released. They specifically would like to know how fast are they moving after they've separated distance h. Okay? So that's what we're going to look at. I want to start by using that blue line as our reference and reminding you that there is the potential to have two forms of energy for each object. There's no spring in this problem, so I'm not going to worry about talking about elastic potential energy. And I'm just going to try and evaluate what form of energy exists for each object at each state. So object 1, state 1. Does it have gravitational potential energy? I'm going to base that on the fact of whether the object's at its highest or lowest point when I compare state 1 with state 2. When I compare state 1 to state 2, box 1 descends, suggesting it has currently gravitational potential energy because it's above its lowest point. Any question about that? Okay. Box 1 does not have kinetic energy when it's first released because it's not moving. In the same way that box 2 doesn't have kinetic energy right when it's released because it's not moving. However, box 2 is currently at its lowest position. So at state 1, it does not have gravitational potential energy. Now, if you're not drawing pictures of the two states, you're not going to do well. I don't think you can do this particularly well, especially if you are new to this, without figuring out what state 1 looks like compared to state 2. So if you're trying to save yourself time, you're just making it worse for yourself. Now, when I look at box 2, and I start looking at the energy it has after, I want to notice that box 2 is moving upwards in state 2, while box 1 is moving downwards in state 1. The direction of motion doesn't matter, but the fact that they're both moving means they both have kinetic energy in state 2. But box 1 does not have any potential energy in state 2 because it's at its lowest position, while box 2 does have potential energy. It is now moved upwards, and so work was done against gravity. It's now storing gravitational potential energy. So I think I can compare state 1 and state 2's energy. Actually, I'm not going to write it over there. I'm going to write it over here. State 1 and state 2's energy. State 1, I have mgh1. That's the amount of energy that box 1 has relative to its position in state 2. That's it. That's the only energy that exists at state 1. But in state 2, box 1 has kinetic energy. I'm going to write that as V1 squared. V1. Box 2 has kinetic energy. I'm going to say it's moving up at V2. And box 2 has potential energy, mgh2. All right, let's get rid of all this. Make it a little bit cleaner. And there we go. That's the energy statement. Now, you can't leave it like this, because we can't have H1 and H2 or V1 or V2 like this in our answer. I might be able to have V1 and V2 as long as we know that they refer to the velocity of block 1 and the velocity of block 2. We can't have H1 and H2. We can only have H in our answer. But I don't think that's going to be a problem. Looking at this system, it shouldn't be hard to discern that H1 has to equal 2 times H2. That if I pull out 1 meter of rope downwards, I'll get a half a meter on either side of the pulley that's holding on to object 2. Any question about that? Yes, sir. Yeah, if you pull out, if we have to pull 1 meter of cable outwards, downwards, well, that 1 meter will come directly from this side, but that will spread out so that there's half of it on this side and half of it on this side. And that's because this whole thing can move. Now, if it was forced to stay still, that wouldn't be true, but that whole thing can move. Yes, sir.
So does that mean that what we have defined in this problem as capital H would be 3 halves H1?
3 halves H1.
Because you have the full H1
maybe,
and then half of H1 substituting it as H1.
I can do algebra, thank you. I would say that instead of saying it that way, not because I'm trying to be difficult, I would say you should be able to make this statement, and then any substitution related to that statement you can also make. You follow what I'm saying?
Yeah.
Okay. But this statement has more implications. If H1 equals 2 times H2, then V1 equals 2 times V2. That has to be true as well. In fact, if you needed it, and I would encourage you to consider why I would say this, A1 would have to equal 2 times A2. I'm saying that because it wouldn't be a bad idea for you to figure out what the tension in this cable is. If I were asking this as an FRQ, I certainly wouldn't stop just at energy. I would definitely want to know tension in the cable, acceleration of the system, all sorts of other things that are acting here. I think the acceleration in this system and the tension in this cable is an interesting question. And if I think it's interesting, it might be interesting on Wednesday. Is there any subtext there? I hope so. Now, once we've done that, this just becomes a bunch of substitution. And that's what happens next. I'm going to cancel out all these M's. We don't need them. And I'm going to substitute, I have to pick one direction or the other. Because of the way it's already solved, I'm going to substitute in for V1 and H1. And write this as GH2 equals 1/2 times 2V2 squared plus 1/2 V2 squared plus GH2. And I forgot the 2 here. There's a 2 there. When I substitute 2H2 in for H1, I get a 2 right there. Questions about that? Now, I don't want it in terms of H2 either, but I will point out that if I substitute here, I'll get 3H2 equals H. Now that's something there. I can get this in terms of H now. So let's do that. That's going to be G times H over 3. I'm just subtracting this from this side and then substituting in H over 3. I can combine these together. 2 squared is 4, half of 4 is 2, 2 and 1/2 is 5 halves. So this is 5 halves V2 squared. And it seems to me that we're kind of done now. V2 squared equals, just multiply across 2GH over 15. I mean, I know some people like this to be cleaned up, so let's go ahead and take the root. And V1 is just going to be twice this. There it is. That's it. Yeah, that was not bad. Not bad. I think, one of the things that's missing from a lot of you guys is just draw it out. Consider what's happening. Without this, you're lost, though. You can't do the problem. And this too, obviously, but really, you need all that. Those aren't physics. Yes, sir?
I know this is like kind of like off of what we were doing, but what if since the two masses are identical, like why doesn't it like instead of it accelerates down, why doesn't it go up? Or why doesn't the block one go up instead?
So, just so you guys know at home, I'm getting a question from a student who's asking, why does it go this direction? Why does block one go down and block two go up? Why doesn't the reverse happen? I don't think we can study that from energy. I think we can only study that by talking about force. So I think you would have to look at the forces acting in the system to determine which direction this would go. And I'm willing to do that here in just a minute, but let me make a couple of statements here that I think should bear some repeating in your notes. And not just you. I think this is for everybody. There are limits to what energy can tell you. One of the ones that probably hasn't been discussed, and I probably need to emphasize, is energy can't tell you the direction of events. Now, that's one of the things we're noticing here. It shouldn't be lost on you that in every case where we solve for velocity, we've had to take the square root, which means truthfully, in every case where we solve for the velocity, we do not know what direction the system is going because we had to take the square root. Energy doesn't tell us the direction of events. More importantly, what's interesting is energy doesn't actually tell us what direction the energy gets transferred. This is something known as first law of thermodynamics and the second law of thermodynamics, that the direction that things occur in nature can't be predicted by conservation of energy. It has to be predicted by something else called entropy, that systems go to states of more disorder and not states of order. For example, it could suddenly happen that a beverage sitting on your desk could suddenly decrease its temperature and start to move. That wouldn't violate conservation of energy. It would violate our observation. That never seems to happen. The reverse happens. But it wouldn't violate it. Why can't the molecules together suck some of the energy out of the system and start moving in an organized fashion? But they don't do that. It wouldn't violate conservation of energy, though. It just doesn't happen. I know that if I heat up one side of a piece of metal, eventually the whole metal will be hot. But for a time, one side will be hot and one side will be cold. Well, why can't a piece of metal that's just sitting there suddenly get hot on one side by getting cold on the other side? Well, that doesn't happen. Why doesn't it happen? It doesn't violate conservation of energy. Conservation of energy can't tell us what direction events occur. But there are events that just don't seem to happen, even though they don't violate conservation of energy. Same as this is the same. I really can't tell you what direction the velocities are. I have to find another way to do that. It is just as, not possible, it is just as the energy would work out just the same if box 2 was going downwards at half the velocity box 1 was going upwards. It would not violate conservation of energy here at all. So if I want to find out why it goes this direction, I have to use a different principle in physics. This one doesn't tell me. And that's something that you guys need to have in your notes, that energy can't tell you direction. It can't even tell you which of these two events occurred first. That's the problem with energy, because time isn't here. And I said that from the beginning. Energy doesn't tell you how long it takes for an event to occur. What I didn't happen to mention is energy doesn't actually tell you what direction events occur either. These events occur due to a thermodynamic thing called entropy. That's the direction that events occur, to create more states of disorder. This system is becoming more disordered as it starts to move, not more ordered. And that's why it occurs in that direction. But we don't teach thermodynamics to high school students. It's too bad because it's kind of interesting. We used to, but not so much anymore. So let's figure out why it occurs in this direction. And this will help all of you when I said you should be able to figure out how to deal with the tension in this problem. There is a downward force mg acting on the cable. Now, I believe the tension upwards is less than the weight downwards. I believe that because I have to rationalize this and compare it with what's happening to box 2, which has an identical downwards vector of mg, but is going to have twice whatever this is acting upwards. No matter what, there is no way it can have 2 times the tension acting upwards and accelerate downwards based solely on that property alone. It's possible that it could, not go anywhere, but I don't see that either because it's got 2 times the upward force acting on it compared to the other boxes only has 1 times that upwards force. The only rational possibility is that the upwards force, being twice as big, exceeds the weight, while the downwards force, being half as big, doesn't exceed the weight. Because it has to be a single tension with a single value. That's why it seems to me that box 1 is going to have to go down and box 2 go up if they are the same weight. And they are. Now, it's possible that I could weight box 2 and force box 2 to go down at the expense of box 1 going up, but they wouldn't be able to do that if they had the same downwards vector. You follow along so far? Now, I think, of course, that you should do this problem. I think you should say that the net force equals MA1 and compare it to the net force equals MA2. And I think you should recognize that A1 has to be twice as big as A2. And I think you should figure out what that tension is. I think you should. But don't listen to me. I'm not going to put the answers for that. But if I was wanting to be prepared for Wednesday, this is something I would look at. All right. I have yeah, I'm listening.
I have a hypothetical question.
Oh,
So,
fantastic, because I love those.
what if you had a similar system, but reflected over box 1? So now you would have 2 tensions acting on box 1.
I'm not going to try and fool you into believing I have any idea what you meant by reflected over box 1.
So, say that you have a similar system arranged on the left side of this pre-existing system. So now you have another box on the left side with a dangling pulley here. Yeah, like that. So now you'd have 2 tensions acting on box 1.
I don't
What
think
would
this
be
system's
the
going to
state of the
go.
system?
I don't know. Why don't you work it out and tell me?
Okay.
This isn't Stump Mr. Shelton Day. If I look at this system, I have reason to believe it might not go anywhere if all the masses were the same. You following me?
Yeah.
I would not state that without, first having taken a good look at it and probably do the net force work on it. But there seems to be every reason to believe that this system would probably end up balancing because everything's a 2-to-1 ratio across the board. So, I got twice the tension acting on box 1 and half as much, the tension's also actually, I have 2 tension forces acting upwards on box 1. Remember, the tension here is the responding force. You know what I'm saying?
Yes.
So I think this is all going to balance out. But you work it out. See what you get. Do that one first, though. All right, I have, since we're asking hypothetical questions, I have a hypothetical question for you. All of you, actually. Here's my hypothetical question. And I'm going to start with a bit of a picture here. This is a super common physics question. It's in every single textbook. And since I saw it in your homework, I went ahead and assigned it. It is your last homework question. So we're going to work on your last homework question together. This was a real thing that they used to make for children to play on, by the way. In places where it gets cold, they would make these ice domes, and basically it's just a slide for kids. So they'd etch stairs into one side so that a kid could make it to the top, and then they could slide off. The problem is that when they go to slide off, they actually can't stay in contact all the way around. They tend to fly off. What I'd like you to tell us, or tell me, is if this has a radius r, at what angle do the kids fly off? This is a conservation of energy question. It's a classic physics thought experiment, one to which you can get an angle for an answer in degrees. Your problem in your book is nice enough to break this up into 3 parts. I wouldn't be. I would just want my angle. But tell you what, because we have what looks to be like 9 minutes left, you have 7 minutes to find V as a function of R and theta and any fundamental constants you want. I would like to know how fast they're going as a function of the angle. I will let you work together at your tables, but I promise I'm going to pick on one person to tell me what V is. You guys at home, I'll be happy to provide you with some breakout rooms. So if you want to go talk to somebody and talk it out ahead of time, then you just jump in there. If you don't want to, you want to do it on your own, I understand. So I've opened up some breakout rooms for you. You have 6 minutes left.